Hi, everyone. Welcome to another episode of Data Dialogues. I'm Julian Redmond, General Manager of Certus Insight and your host. For this third and final episode featuring the content from the 2021 Worldwide Data Vault Conference, we're going to look at the laws of nature and what they mean for information management. Our very own Certus Data Vault expert, Nols Ebersohn, delivered this presentation, which looks at the laws of nature for information, the consequences of these laws, how it changes the way we approach information management, and in particular, how these laws affect your data vault. If you'd like to learn more about the laws of nature related to information management, I recommend a series of blog posts Nols has written. The links to those blog posts can be found in the page below. But for now, here's Nols' presentation.
My name is Nols Ebersohn. I'm a principal architect at Certus Solutions here in Australia. Been doing Data Vault for a little while, and I've been honored to present once again at this year's conference. And hopefully the topic at hand will be a good thought provoker and sort of revisiting a few definitions, revisiting a few things, and then looking at some of the implications it has within the Data Vault context. Just a quick little bit about Certus Solutions themselves. It's an organization. We deal with information management as a major focus. We have an asset-intensive business arm that deals with a lot of utilities, power, and other asset-intensive businesses and helping in that regard. We have information and insights where we do the analytics in the Data Vault kind of initiatives, including master data management as such, governance, data quality frameworks, and the like, which then further extended or augmented with digital business services and design services as well, for both a business process perspective as well as technology and information. We're based in Australia and New Zealand, so this is a fresh in the morning for us here in Australia, but hopefully it won't show. So here's a couple of things that I want to sort of explore. We understand that we have laws of nature, things such as the law of gravity, the law of conservation of energy, thermodynamics, and more. So we have all of these laws. We're reasonably familiar with these laws. And so these laws allows us quite a bit of stability in what we do. And the reason why that is the case is that a law of nature is a precise statement that is based on observation, discoveries, and experiments that is repeatable and verified. And this is really important from an overall design perspective. For instance, if the law of gravity was not constant, then driving a car would be a very different prospect than what it currently is. To go down the road, to go to the grocery store, for instance, you may have to deal with a three-dimensional travel as opposed to just the standard travel to a destination. And what this really helps us to do is, because those laws are universally valid, they do not vary in time, they are typically very simple, at least at a conceptual basis, and there are no exceptions. And this is the important part. As been mentioned by a number of the other presenters before, the correlation is not necessarily causation. In other words, if something seems to be correlated, doesn't mean it's universally consistent. And so from that perspective, the law of nature helps us to govern the way we approach our design. Now, there's a couple of categories of things in law of nature, and we know that we've got at least things like matter, information, and life. And why is that important? Because matter, we've got very well described. We've got all of our physics, we've got all of our scientific endeavors recognizing these laws and abiding by these laws. And so from as far as matter is concerned, it is very well described. As far as the life is concerned, the only scientifically verifiable, reproducible law that seems to be universally available is being what Louis Pasteur defined the law of biogenesis, or life only originates from life, because that's the only thing we can observe. It's readily observable that matter exists, and that's so it's essential for our existence, and life as such is reasonably observable, and it's essential to our life, etc. But we also know that information exists. But the laws of nature for information has been eluding us for a little while. So, and as far as the research and what I'm going to present today is relatively new. It's only in the last few years that this has been defined. So this is an interesting take and an interesting perspective on it. So what are these laws of nature that governs information? Because information is an interesting animal. It is a very element that seems to elude what it is, because what is this? What is information? It's sort of an existential kind of question. What is information? And as Norbert Wiener stated, information is information, neither matter nor energy. It is an entity in its own right. For instance, we can have information about a particular product, and it doesn't care where it's stored or what it's run on, whether it's on your Apple Mac or whether it's on your Android device. The matter that actually exists doesn't really govern or constrain the existence of the information as to where it can exist. So this question about information, and given that we're in the practice of information management, is perplexing, because for what seems to be such a simple concept, or at least an elegant concept, not necessarily simple, but elegant sometimes hide the complexity that comes with elegance. The problem we face, though, is the way we've defined information in the past has not been precise. So this is like taking a shovel, using some of our previous conversations, and doing brain surgery with it. Is it possible? Perhaps, but is it advisable? Quite not so much. And so from that perspective, we need to get a little bit more precise in what information is, so that we can therefore treat it and understand where it fits and what its implication is in a broader sense. So Professor Werner Gitt, or Dr. Werner Gitt, is a professor of engineering at the Germany's Physics and Technology Institute, is the first person that has provided a scientific definition of information, and essentially defined information to require at least 5 levels to be satisfied to be true information. You basically have defined these 5 levels as statistics. In other words, you need to use something consistently as a symbol for a particular idea. Syntax, in other words, it needs to appear in a certain set of patterns for it to exist within a set of constraints and rules. It needs to have a meaning, semantics. There needs to be some sort of expected implementation or action that goes with it, and so the pragmatics come into place. And then there needs to be a purpose. That fundamental why question needs to be answered, and this is where the term apologetics were born, to essentially capture the purpose of that. So these are the 5 levels that are required to create information, but this is the full scientific definition for it. And perhaps this diagram here, it seems to be complex, is at the heart of the challenge that we faced thus far. There is complexity. It is not able, we're not really able to distill it or munge it down to anything less, because you need a sender of information, an origin of information, and you need a recipient of the information. Otherwise, why bother? Why does information exist unless there is a sender and a receiver? And these needs to be, the transmitted signals need to be received, and it needs to be understood. And the meaning, the semantics needs to be consistently there for the actions that are expected to be actionable. and then the whole reason as to why this exchange occurs needs to be unpacked. So from that perspective, we've got a number of complexities that are encapsulated here with the elements that constitutes the information as a definition. Now, typically what we've done in the past is simply said, you know what, those first two levels is what we typically regard as data. Fair enough. It's encoded, it's statistically consistent, and from that perspective, it becomes data. For instance, this transmitted signal or the codex that is going around with it is as simple as this. Consider that who said 1 is 1 and 1 plus 1 equals 2. And so from that perspective, the symbolism, the code that is being used to encapsulate the concept needed to be consistently used for it to become a set of data. If we then add what it means and what we expect to do with it and what the purpose for that particular information is between the sender and the receiver, that is what we classically consider to be context. And I know there's been quite a bit of debate, and I perhaps have been an instigator of some of those conversations, but this, what is data and what is context, is important because it's a combination of both context and data that actually creates information, that constitutes information. So unless you have all 5 levels satisfied, you don't necessarily have information. What do I mean? Let me demonstrate it as such. Cal Sanford, I probably pronounced the names poorly, so apologies for that, is a nature photographer, and he found all the letters of the alphabet and all the decimal numbering representations, symbols, and he went across the world and photographed these symbols and letters on the wings of butterflies and moths. And you look at it and go, well, that's fantastic, colorful, all the rest, but it's just data. There is no purpose around this. There's no message. There's no semantics around it. There is no expected action as such. This is incidental data that has been correlated to each other as a set of photographs, and that's about it. So from that perspective, this is a good example of just data. It's not really information because it lacks that other components to it. Here, however, is an example of information, but it was but just data for a long time. So the Egyptian hieroglyphs were clearly visible on all of the Egyptian buildings, and we see that it was repeatedly used. That's the statistics. And it was used in certain combinations. That's the syntax, but we had no idea what the actual meaning was. And it's only when the Egyptian alphabet was untangled, when the discovery of the Rosetta Stone was made, that the actual semantics and the message was therefore being able to be decoded, understood in due time, which then means that the message that was intended by the sender now becomes readily available for the receiver to consider. And this is the interesting thing. There can actually be a time lag between when the message was sent to when the message is received. Let's just say with a reasonably strong confidence that the original carvers that produced the Egyptian hieroglyphs are no longer around or available, or neither is the pharaohs, to essentially underpin an active conversation, yet information is readily available. So that gives us a little bit of an example as to you need all 5 of the levels to be satisfied to actually have defined information, actual information. So this defined what governs the information. What are the laws that govern the information? And so we're going to go through a few laws here with the supporting examples to sort of give you a bit of contextual background. So the first law of information is nothing material or chemical can in fact create a non-material entity. Here's a good example. We can gather all of our hardware, our disks, our motherboards, our computers, our networks, we can all gather it in one spot, but it means nothing. It does not produce information by its own existence as such. It needs to be configured, it needs to be designed, there needs to be an input to all of this. It needs information to exist outside or separate to the actual physical or chemical processes for this to in fact work. That's why we install an operating system on a computer, for instance. The hardware means nothing until you bring the information. And so this information then leads the fact that it cannot exist as a or be generated by a physical or chemical process. Information is a non-material fundamental entity and not the property of matter at all. As was stated by our mathematician friend, information is information, neither matter nor energy. So the information is encapsulated, whether it's in memory or on disk, but the information requires some of that matter to exist, but it is an additional part. It's a fundamental different element, which then brings us to the third law, which information requires a material or medium for storage and transmission. All information to be readily available needs to hit the disk, so to speak, at some point in time. If you have virtual fields in your applications and you need that information to be available to your analysis, to your analytics, to your machine learning, if it's not in the data, it did not happen. And so you either have to have the application not provide that virtual field or those calculated fields as an artifact, or you have to replicate that functionality by business rules to produce that artifact so that you can then integrate and exchange it to other business processes. So this is actually a fundamental element, because guess what? Business processes change. Applications change, architectures change, technology change, business design change, organizational structure change. The only thing that remains consistent throughout is the information that's stored on disk as such. And so this gives us a really important view on what it means to have longevity of your information set. Another good example of this is you have an oral tradition where a tribe may tell stories and legends to bring a particular set of history through. But that dies out when the person that was sharing the stories dies as such. Unfortunately, death and taxes being the two certainties we deal with, we need to understand that that's a risk. This is why the Egyptians have invented the hieroglyph. Their method of recording the information for a longer sustainable period. And so to transmit information, it's really important to have a medium to store it on. And probably one of the most fundamental storage, the most densely dense example of information is DNA. DNA is fantastic. If you take DNA and string them out, because every cell that has a nucleus has DNA in it. If you take that DNA out, it's in a little ball. If you unwrap that ball, it'll stretch for 2 meters. A single cell's DNA, if you look at the information density in it, it's 27 million times the information encapsulated in the entire Bible, just as an example. Then consider that you have about 7 billion cells in your body. Now that's big data. Yet we do not have any issues with being able to pass that information on because there is a storage medium. There's a way to integrate it. The next law of information is information cannot originate in statistical processes. And this is where we go, hang on. What about machine learning and artificial intelligence and so on? And the counter to that question is, well, that's great. You can have machine learning and algorithm there, but it needs a purpose. Remember, we have 5 levels that needs to be met to have full information. It starts with a hypothesis. It starts with a use case, an expected action, expected optimization that comes out of that process. Then we tune and tweak them as we go along to get the appropriate result. So even though we have statistical processes, in and of themselves, they do not create information. They need an intelligent design input for them to be effective. You cannot have information without code, which goes without saying, given the 5 levels that we have. If you have no language on syntax, there's no understanding. If you do not have a business glossary, how do we actually manage the conversation within our business? Now, these are real examples that we struggle with on a daily basis. We rely on our contextual shared experience to help bridge some of those gaps, but it's flawed by nature. Law number 6 says that all codes result from an intentional choice or agreement between sender and recipient. If this presentation was supposed to be presented in English and I break out in Xhosa, which is a native dialect in South Africa, then clearly most of the audience will be lost because there's a tacit agreement between us that this will be done in English, in a syntax, in a code that we both understand. And so the laws of information is now helping us to understand how those 5 levels of information starts to play out. So the determination of the meaning for and from a set of symbols is a mental process that requires intelligence. It's all great. We can teach an orangutan or a chimpanzee sign language because there is a measure of intelligence present. However, not so much for a snail. And so there is a level of intelligence required to understand this symbolic representation of the reality that we operate within. We all natively understand or inherently understand that 1 + 1 is 2, but that conceptual, that symbolization of it is in fact an agreed intelligent measure of how do we interpret or symbolize the elements around us. Which then brings us that there has to be, for new information to exist, needs a purpose, and it needs an intelligent sender for that purpose to exist. Think about business rules, right? Why do we bring a business rule to the table in our data warehouse, in Data Vault, Business Vault, etc.? It's because we're trying to resolve a gap, a technical debt that exists. Now, from a technical debt perspective, to resolve it requires careful thought. It requires design. It requires agreement between the business and the team as to how to go about doing so and what is it used for. And so those contextual elements needs to be available, and the agreement around that information needs a particular purpose. Don't worry, we're nearly at the end of the laws. The 9th law is any given chain of information can be tracked to an intelligent source. Every book has an author. The author doesn't have to be present. You can have Aristotle writing articles from way back when, and yet we are able to consume those elements, that information, that communication from a number of centuries ago, and take it from there. Every sentence we utter originates from a measure of intelligence. Well, sometimes. So it's one of those things, right? Sometimes we sound brilliant and the other times not so much. So hopefully this all makes sense. And the last law of information is that it is the non-material foundation for three different types of systems: technology systems, works of art, which includes music and even visual arts, and biological systems. That's where we find information is communicated. You can go, hang on, what's this works of art? What's music? Well, here's the thing. If somebody comes along and says, we need a bigger boat, and they play that particular jingle of jingle bells when that statement is made, it doesn't really resonate. But if that same statement, we need a bigger boat, is made with the theme music of Jaws, it changes the context, the message, the information entirely. So works of art, in fact, communicates an emotional communication medium that is otherwise not possible. Just a different frame or different mechanism of delivery of information. Biological systems, we've mentioned DNA and those type of things as a representation where information is very much at the core. And clearly, given it's a Data Vault conference, technology systems is very much in focus, and we understand that it contains information. So this is sort of the fundamental laws as such. Now, these laws of nature, you can test them. For them to be laws of nature, you need to be able to demonstrate that, in fact, it remains consistent and true and precise along the way. And thus far, I've not yet been able to find any challenge that cannot be met by these laws. So we've defined information, and we now need to know how we govern information. But what does information consist of? The laws of nature exist, that's great. The definition exists, but it also requires building blocks, components. And so for matter, we know this. We've got electrons, protons, and neurons, and great, we can describe all matter around us in various combinations of these to determine whether it's lead or gold, for instance. Music has three components to it. You got melody, harmony, and rhythm. And you can describe all the music we ever encounter by virtue of those three components. We can do the same for time, past, present, and future. We can do the same for the universe. Time, space, and matter. These are all the building blocks, the components of what we know about our environment and our world. And for information, we know that we essentially have the fundamental building blocks or components of having business keys, relationships between those business keys, and then the descriptive details that describe either the business key or the relationships. And so from this perspective, we now look at all of our information, and we can take these fundamental three components, design a system around it, and therefore deal with all the information we can ever encounter, all the data that we can ever encounter in our organizations as such. So these fundamental building blocks hold true. Now, for those already initiated into Data Vault, you can recognize where that particular statement holds true. So now we have information that is defined very precisely in a fairly concise but somewhat complex definition. We know what governs it, the laws that govern information. We know what the components of it is. Now, is the same thing that exists for matter, for instance, applicable to information? Does it have a consistent state? So, for instance, we know that matter can be described as solid, liquids, and gases. And so, does this apply to information? And in fact, it pretty much does. Random codes, or the gaseous state of information, is random codes exist, but they exist within the rules or within the patterns that exist, like prime numbers in math. We have data, and we've already seen that the first two levels of information, the first two levels of the definition of information is what we classically call data, and call it water because it's somewhat fluid. And then information is where it is at its most solid. And there's essentially these states exist. So within a cellular body, we know that we have information because we have the exchange of information happening between cells and between processes. As a cell divides, not only does it divide and make a copy of itself, it has a reconciliation process that double checks that the copy was in fact successful. If there's any reconciliation problem, fixes the reconciliation problem, and then only allows it to propagate. And if it cannot fix it, it will terminate that particular copy and do it again. And so we have this complex set of processes, business processes, rules that govern that particular set of activities. And even within a song, right? If you want harmony, the one note needs to follow the other note in a harmonious sense. And therefore, otherwise, you do not have a tune, you have noise. In our applications, we have business processes that need to integrate, and at the boundaries of those business processes, they exchange information because there's a purpose, there is an activity, there is meaning, there is the syntax, and the statistics are all wrapped up within those systems. The challenge we face, and this is the fundamental information management challenge that we face, is the moment that the data leaves that ecosystem, the purpose, the meaning, and the actions become a challenge, in that if we do not capture it in our metadata, we lose that context. And that's our challenge. So if we look at a very simplified architectural flow here, we note that we have a decent set of information in our source systems, because those source systems, those business rules, those rules in their orchestration context, in their dependencies that they have been met, all of them have a particular purpose. They deliver a particular set of values, particular set of functionality. It's good information. The moment it leaves the source system, it becomes data. It changes state. That's why we call it a data vault and not an information vault. So the data vault then captures all of that information. And it's no different to what we have, for instance, or the data as such. It only remains as information when you actually have a consumer. So it goes from information in the context of the applications, reverts back to data, which is the minimum viable product across time, and only becomes information when there is a user, a consumer of it for a particular purpose. Next best offer. Optimization from the business process, tracking against budgets, all of that information consumption side of things are essentially returning it back to an information state. Hence, we're calling it information marts within the data warehouse or data vault architecture. Now, of course, things are not always that simple. As we can see, this metadata element that we have at the bottom needs to be intact. We need the lineage. We need to be able to describe it, define it, assign an owner, have stewards that look after it, maintain it. We need to make sure that it's known as to what and when can you use it for, why do you need to have it available, and what action should you take on this. And without that context, this consumed information, when we have the conversation between the sender and the receiver, we need all of them to exist in those 5 levels for it to reconstitute as information. And this is the challenge. Now, we've heard a number of other presenters also speak to the point of you need a taxonomy, you need an understanding from the business, you need the semantics to be clear. You need to be able to understand where it comes from, what it's useful for. The challenge we deal with is we have gaps in the actual information that exists. Some of it gets lost along the way, and so that's a challenge. So we need to deal with the information or the contextual losses that we encounter and see in our implementations. We also need to deal with the things that are fundamentally missing or broken. And this is where our business rules, the soft business rules, come into play in the Data Vault architecture. They are dealing with the gaps. And as Richard mentioned this morning, a machine learning algorithm takes in data and just produces more data. Yes, it's a score. Yes, it's derived. Yes, it has a different purpose. It's typically an optimization, a discovery of a new relationship. But the bottom line is all of that is a derivative of the data. It kind of gets a little bit information-y because you clearly have to either recreate or create some sort of context for that particular business rule to execute on, but the result is just more data. Because it's data, the data vault deals with it, and we essentially have that sparsely populated business vault elements that helps us to integrate the missing information back into our overall data vault, so that when we come to information marts, when there is a particular purpose that we want to look at, that it can then draw the sender and receiver together and provide the necessary metadata, meaning semantics, security, on top of that, to essentially help you to reestablish that information context properly. And of course, information marts and so on has some functional rules. In other words, security is a good example. Time management, because sometimes we need a report quarterly, and sometimes weekly, sometimes hourly, or whatever the case may be. And so there may be some functional rules, but fundamentally, it's not creating any new data. Whereas your soft rules will be creating new data and using the same inbuilt versioning that is inherent to the raw data vault patterns or the data vault patterns per se. We don't have to keep every version of every rule we've ever encountered in our business rules engine if we have the results. And in fact, as discussed this morning, it's impossible at times for machine learning algorithms to get the same result run at a different time. And so to mitigate those risks, having a record of the actual outcomes then benefits from exactly the same historization, exactly the same management framework that is afforded all of our upstream raw source data sources as such. So leveraging what is already there inherent in the architecture makes it available to your information marts, but you have to manage your metadata. And metadata becomes even more important in the data vault context because, frankly, without the configuration metadata, identifying what is a business key, what is the relationship, the unit of work within the relationship, these type of elements become less automatable. And so metadata plays an absolutely crucial role. The classic use case for metadata has always been lineage. And yes, that is true. That is necessary. But you need to be able to overlay it with your information management policy. You need to be able to overlay it with expectations, quality expectations, so that your data quality rule sets can produce a score for all of the information that may exist in your vault so that you understand the state of that data. Because frankly, we do not know what the data quality score for our information is or our data is until such time as we evaluate it. We run a rule against a standard to establish that particular context of the data. But again, the data quality score is but more data. The only time it becomes information is when we have a receiver with a purpose around it as well. Now, we can say, you know, this is a very tall order. This is interesting and this is fine. We can understand that there is, in fact, a change of state it exists in a context and so on, and it's information in our sources and becomes data. It is the minimum viable, survivable product that we have. It needs to be on a disk of some sort, because if it's not in the data, it didn't happen. And then we can reconstitute it as information as long as we bring the appropriate context with it. So where do we do this and how do we do this? And this may seem like a tall order. That is not as big an order, tall order as it may exist, because the technologies for most of this metadata management already exist. So you can have process automation because you have the metadata. You can have compliance and data governance taken care of because you have the metadata. Who owns it? What is the expected quality expectation for a particular element? It needs to be rapidly able to deal with change, and this is the benefit of the componentized management style of Data Vault, in that we're dealing with fundamental building blocks which do not change, and therefore our processes remain consistent, but we can just configure more inputs to those processes to be made available in our Data Vault. It needs to be able to do any scale with, and so they start small, end-to-end. Iterative delivery needs to be encapsulated and supported. You need to have it secured, and you need to be able to reduce cost over time, because this is your challenge. Data warehouses have but two jobs: integration by business key of your information and recording the facts in the time context. That's the job of a data warehouse, period, nothing more. In as far as the challenges for the data warehouse is concerned, is it needs to be able to deal with the technical debt, and being able to insulate it and encapsulate it. We can manage it more specifically because you have more than one business rules engine in most organizations. And you also need to deal with the fact that any re-engineering needs to be mitigated. Now, for those that are familiar with Data Vault, which is most of the audience, we know that these elements are well and truly delivered on. So in Certal Solutions, we've looked at the full information management package and understood that clearly there is a people, process, and technology element, and have provided a platform as a service that allows you to do all of those elements. All you have to bring is the people component, because the process components are already encapsulated in best practice playbooks and test harnesses and workflows associated to deploying a successful data warehouse environment. It is underpinned by some capable technologies that you may recognize as such. It also extends it beyond the basic automation metadata in a full glossary governance framework with stewardship functions, support for business process components to that, reference data management, profiling, and service level agreement and procedures, all encapsulated in it on a number of different storage platforms. So what seems to be an insurmountable platform challenge is in fact already available from a technology perspective. And why do we want to make this available? Is so that the actual consumption, the actual usage of your information is fast-tracked as best as possible. So all of these implications that we've looked at, the laws of nature for information, dictates that we need to define our information definition precisely so that we understand when and where the information changes state from information to data to information. It helps us to understand the building blocks that are in place. It also helps us to then see the value and the design paradigm that Data Vault brings to the table to leverage those underpinning components and elements without creating further problems or legacy elements as such. So these things are possible. They have been done before. They are well known and understood. And so the implications for these are important. Now, as far as the business rules are concerned, and this is a bit of a hobby horse for myself, in understanding this fact that information, the business rules that we do is in fact just creating more data, because all of our source systems, all the business rules encapsulated in it, creates just data. And so from that perspective, business rules just creates more data, and we need to bring that context fully in through our metadata as such to make this useful overall in the long term. Can we get away with some of these things as potentially, for instance, business rules being virtual? Yes, you can, absolutely. You can virtualize those elements, but the moment you make a decision on those, the moment you have a change in version, if you do not have those results readily available, you're now building up a body of work that needs to know every business rule for every version ever, regardless of technology. And therefore, it does create challenges in supporting and maintaining it. We do not keep every version of SAP that we've ever had in an organization. We only have the current one, because the data that is encapsulated is already representing those versions, past versions, reliably and consistently, with a high level of audit and reconciliation. So why don't we do the same for business rules? So these are the challenges that we need to consider. These are the architectural options that come from it. We know that for information to be exchanged at a level that continues to scale and continues to expand, you have to consider that information requires matter for it to be stored upon. And in our space here, it means that it needs to exist on disk at some point.
Thanks for watching today's episode of Data Dialogues. It's amazing how the laws of nature actually apply to information as well. I hope you found it as interesting as I did. The next episode will be a Data Vault Masterclass, so keep an eye out for the link for that in your email.